Okay, let's talk about series circuits, specifically resistors in series. So there's a lot of different ways you could draw a diagram, and it doesn't really matter how things are turned or oriented, but what does matter is what is connected to what. So I'm going to draw the battery on the left side, but again, it doesn't really matter where I would draw it. This is the positive side of the battery, and I'm going to draw one resistor connected to that. That first resistor is connected to a second resistor, which is connected back up to the battery. So this is actually the same circuit as this one that we drew on the Kirchhoff's laws diagram, where we've got a battery connected to one resistor, which connects to the next one, which connects back to the battery. Even though I drew this in a different orientation, it's still the same circuit. Let's look at an actual physical setup of this circuit. So the connections that we see on here should be the same as the connections that we see on here. Now, I don't have the actual battery plugged in, but besides that, everything is set up correctly. So the positive side of the battery connects to the first resistor. That is this connection. The positive side of the battery is in this same row here with this resistor, row 10. So it connects to this resistor. That resistor is then connected to the next resistor. So this connection here is the same as this connection in the row that's labeled 15. And then the second resistor is connected back to the negative side of the battery. That's here in row 20. Our second resistor is connected back to the negative side of the battery. So we have our three connections: battery to our first resistor to the second resistor, and then second resistor to the battery negative. And those are the same three connections that we see on here. First connection, second connection, third connection. It's important to know that things are connected if they're in the same one of these little rows of 5, but it's not like the battery positive is directly connected to the battery negative. Even though they're kind of in the same long row here, that's not the rows that cause a connection, only if they're lined up this way. Okay. So that's what the physical setup looks like. I'll just leave this here for now. And then let's make a connection to the air demo. So what the current is doing is it's coming out of the battery, which was represented by the box. We had our little, there's our box. It's going through one resistor, and then that same current is going through another resistor along the same path. So this would be like adding 2 straws in a row for the air to go through as it's coming out of the box. And because all materials have resistivity, you could picture both of these straws as having the cotton balls inside of them. So as the air comes out, it has to go through this one, and then through this one. In this case, we can think of this as being the battery positive. This is being our first resistor. This is our second resistor. And then when the air escapes into the rest of the room, that's basically like returning to the negative side of the battery. So we have the same connections here: battery to our first resistor to the second resistor to the battery negative, essentially. Okay. So think about, compared to if we only had one of these resistors connected to the battery. either this one or this one by itself. What do we think the resistance is going to be of these two things combined? Do we think that there's going to be more resistance, less resistance? Is it going to be the same as R1? Is it going to be the average of the two? What do you think is going to happen? What makes the most sense to me is that because the air has to go through both of these obstacles, or the current needs to go through both of these obstacles, the overall resistance will be higher. More stuff to push through. Okay. Ohm's law applies to this circuit in a few different ways. So I'm going to draw the circuit again down here. Okay. So first thing I'm going to think about is Ohm's law for the whole circuit. There's multiple ways to write Ohm's law. I'm going to use the one that's on the reference table, which is R equals V over I. And I need to be specific here because there's more than one resistor in the situation. And there could also be sort of subcategories of the entire circuit for other ones of these variables. So I'm talking about R for the whole circuit equals V for the whole circuit over I for the whole circuit. So the R I'm talking about is the combined effect of these two resistors together. The V I'm talking about is going to be the V of the battery. And the I is the current coming out of the battery. It turns out that the resistance from combining two resistors together has a special name: equivalent resistance. And that gets abbreviated REQ. That means the combined resistance of the entire circuit based on whichever resistors are in there. And then I could write battery, but I'm just going to call these V over I. So if I have a plain V or a plain I, what I mean is the voltage from the battery, the voltage for the entire circuit, and the current from the battery, the current for the entire circuit. Okay. It's also, let's review how Kirchhoff's current law and voltage law apply to this. So the current law says that the current in equals current out. And we don't have any alternative paths or anything like that. So I will be the same everywhere. There's no way for the current to appear or disappear. There's no extra branches or other paths for more current to join or some current to split off. So the current's going to be the same everywhere. The voltage law, you might remember, says that the total amount of V decreases should equal the increases, which come from the battery. And what that means is that there's going to be some energy used up by this first resistor, which we'll call R1, and some energy is going to be used up from this second resistor, R2. So what that means is we can write Ohm's law for each of these resistors on their own, as well as for the entire circuit. And just like R equals V over I for the whole circuit, R equals V over I for this resistor specifically. But this is the individual resistance equals the individual voltage, which we'll call V1, over the current. And we could say it's the individual current, but we know that the current is the same everywhere. This voltage is not the same as the voltage for the whole circuit. It's only part of it because we have some amount of increasing from the battery, maybe it's 9 volts. Only part of that voltage is getting used by this resistor, the rest will be used by this one. R2 equals V2 over I for basically the same reason. And the voltage law tells us V1 plus V2 equals the total voltage. Okay. Because we know when we add up these voltages, we get the total voltage, we could write the same thing would basically be true if we take this equation and divide it by I. So my total voltage needs to be however much is getting used up in the first resistor plus however much is getting used up in the second resistor. I'm going to divide each of these things by I. And then I notice that my total voltage over the current, that's the equivalent resistance. V1 over the current, that's R1. And V2 over the current, that equals R2. So, because of the way that the voltages add up, I get this equation. The resistance of two resistors in series, the equivalent resistance of those two acting together, is just those two resistances added together. This derivation can be kind of confusing, but now that we know this equation, we can use it. So let's get some practice using the equation and then also using Ohm's law for the whole circuit and Ohm's law for individual resistors. Okay. So a 100 ohm resistor and a 50 ohm resistor are connected in series to a 9 volt battery. Find the equivalent resistance, find the current, and find the voltage for each resistor. So this is a few questions combined together because I wanted to show you all the different things we could find. So first of all, let's find the equivalent resistance. Req equals R1 plus R2. which in this case is 100 ohms plus 50 ohms, or 150 ohms. That is our equivalent resistance. Now it wants me to find the current. I'm going to use Ohm's law for the whole circuit, which is R equals V over I. The R I'm talking about is the R for the whole circuit. The V I'm talking about is the V for the whole circuit, and the I I'm going to solve for is the current for the whole circuit. So this would be 150 ohms equals V is 9 volts over I, the current. To solve for I, I'm going to multiply both sides by I, and I get 150 times I equals 9. So then I'll divide both sides by 150, and I'll get 9 divided by 150, 0.06 amps. We got that by using Ohm's law for the whole circuit. We found the equivalent resistance already, and then the volts was given to us. Now let's find the voltage for each resistor. So you might think, what do you mean the voltage is already given? This is the voltage for the whole circuit, the plain V. But because the current needs to go through one resistor and then the other, it uses up some of that push, some of that energy through the first resistor, and then it uses up the rest of it going through the second one. So I'm going to use Ohm's law for our first resistor only. And that's going to be R equals V over I. But this R I'm talking about is the first resistor, so that's 100 ohms. The V I'm talking about is the voltage across just that first resistor. V1, I don't know it, it's not just 9. And then the current is this 0.06 amps because the current through each resistor is the same as the current everywhere. Now I can multiply both sides by this 0.06, and I end up finding that, oh, this should be amps. I end up finding that V1 equals 6 volts. So our current had 9 volts of potential to start with. As it went through the 100 ohm resistor, it used up 6 of those volts. It's got 3 left. V2 must be 3 volts. You could use this equation, V1 plus V2 equals the total V, 6 plus 3 equals 9. Or if you wanted to, you could use Ohm's law for R2 and set up R2 50 ohms equals V2 over the same current. You get 3 volts either way. Okay. Cool. Hope that was helpful. We'll get more practice with this. I know it's really confusing to start with, but you gotta remember when you're thinking about Ohm's law, picture whether you're talking about the whole circuit or just a little piece of it.